Okay, so today we start chapter 5, which is charge carrier transport in semiconductors and the resistor structure. So, indeed, this is the first chapter where we actually use the theory that we have learned so far and form the first device structure. And the first device structure that we're going to start with is the resistor structure. This is the simplest structure, the simplest device, but we know that it's the most important device because it almost comes as part of all circuits. So that's an important device. And then we will progress from the resistor upward. So we'll go to more complex devices. And so we know about the free carrier densities. So we've done quite a bit of that in the previous chapters. And this is very important towards understanding the electrical and optical properties of semiconductors. Why is that important? Because current in semiconductor is carried by electrons and holes, which are the negative charge and the positive charge. And it is carried by the free electrons and free holes, which we call them the free carriers. So the densities of the free electrons and free holes are very important in determining current or the flow of carriers. This flow of carrier or flow of holes and electrons is called transport, the transport of carriers. And this transport or this movement or this flow of carriers generate the current. There are two very important mechanisms, two basic transport mechanisms, two basic ways of how carriers move in a semiconductor. One of the movements or one of the transport mechanisms is due to an applied electric field. So if you apply an electric field to the semiconductor, then the charge carriers move because of this electric field. We know that in an electric field, positive charge moves in the direction of the electric field. Negative charge moves in the opposite direction. So the electric field induces motion. So this is a kind of motion that is induced by an applied electric field, and this motion is called, or this mechanism is called drift. Drift in an electric field. So you need to apply an electric field and then you get drift. So the first mechanism that is very important for hole and electron transport is drift. The second mechanism for transport or for the flow of holes and electrons is due to the changes or differences in concentration. If we take a semiconductor and we know that there is concentration gradient or differences in concentration between different regions of the semiconductor, then carriers, being them electrons or holes, would move from places with large densities to places with smaller densities. This process, which is motion of charge due to density gradients, is called diffusion. So the two mechanisms are: one, drift; the second mechanism is two, diffusion. And these how carriers of free electrons and free holes move from one place to another. So in an electronic device, we need current to pass. So we have to have one of these two mechanisms operating. We need to have drift or we need to have diffusion. we will see that in a simple resistor, what the mechanism that is going to dominate is the drift mechanism. Now, let's talk about current, how we generate current in general, okay, and current density. We will work with current density rather than current, and I will tell you what we mean by that in a minute. Okay, current density is the current per unit area. So current density, and we normally call it J, is current I divided by the cross-sectional area of the conductor. So this will give us current, and the unit will be the units of current divided by the units of area. So it will be something like ampere per meter squared, or ampere per centimeter squared, or microampere per millimeter squared. So it's a density, it's a current over unit area. Okay, having said that, let us think of a cube. Okay, this cube has unit area. Okay, so this area is one unity. Unity meaning it may be 1 millimeter squared, or 1 meter squared, or 1 centimeter squared. The area is unity. And let's say that in this box, I called it a cube, but let's call it a box. The area, the cross-sectional area here is unity, but then the length or the depth of this box is V sub n. Now V is velocity or speed, n for electron, negative. So let's assume that this box contains electrons, and electrons are coming from this left side entering this box, and they emerge or come out from this right hand side. Okay, let's assume that the average velocity of this electrons coming in, is Vn, V sub n. So, and the length or the depth of this box is V sub n. So if an electron comes here at the beginning of time, it will take this electron 1 second to come out on the other side. So every electron that comes here at the beginning leaves out here in 1 second. So that means every electron inside this box will be able to leave out in 1 second. Even the farthest electron, which is right at the back, would be able to leave in 1 second. So all the electrons that are inside, of course, will be able to leave even in less than 1 second. So all the electrons inside this box would be leaving this box in 1 second if we have their average velocity is Vn, which is the length of the box. So the total number of electrons here will be n, which is the density of electrons per unit volume, times the volume of the box. So this is the total number of electrons inside. Let's call it capital N. So this will be n, the density of electrons, times the volume of this box. Now the volume of this box is the cross-sectional area, which is 1, times Vn. So the volume of this box is V sub n. So this is the total number of electrons inside this box. Make sure, we said that all of these electrons will move out of this box in 1 second. So the total charge that will move out in 1 second will be the charge of the electron, which is minus E, times n, which is the total number of the electrons in the box. So this will be minus E N times Vn. So the total charge that will move out in 1 second is given by this. But the charge that moves out in 1 second is current. So current is the charge per unit time. So actually this is the current that moves out, or the current that goes through this cross-sectional area. But it's a unit area, so it's current per unit area. So it is J. So the current density of electrons, N for negative, that goes out of this box is minus En, where N is the density of free electrons, times Vn, where Vn is the velocity. Now look, you see that I'm using bold letters, meaning I have a vector for J and I have a vector for V. So J is the vector, V is the vector, okay? So the current has a direction, it's a vector, the velocity is a vector, okay? Similarly, I could have made the same argument for holes. And if I do that, then the current density of holes similarly will be equal to E, the charge on a hole, which is positive electronic charge, times P, that's the density of holes, times Vp, the velocity of holes. So you can have electron current if you have only electrons coming to this box, or you can have hole current if you have only holes coming to this box. So the basic thing is you need the density of free electrons and you need the density of free holes. So that is why the densities that we studied in chapter 4 are very important in determining the charge flow or the current. But you also need to determine the average velocity of electrons or the average velocity of holes. Okay, so we need these two parameters. So this mechanism, in the first mechanism, so this is general. This is true for any flow, okay, being it drift or being it diffusion. Okay, if we know the density N and if you know the average velocity, then we know the current. Okay, now we focus on mechanisms. So let us talk about the first mechanism, which is the drift. So now we want to have an electric field. Okay, so we have a field, and then because of this field, the charge will move. So drift is the type of transport available to electrons and holes in a semiconductor if you have an electric field applied. When drift is the cause of the average velocities, so what we're trying to do now, folks, is we're trying to determine the average velocity. We need the average velocity to determine the current density. So now we want to use drift, that is an application of an electric field, and try to find this velocity, because as you can see, I have velocity here. Okay, I need these velocities. So let us apply an electric field and try to determine this velocity. So we're going to consider situation in a semiconductor where it's in thermodynamic equilibrium, which means that there is no voltage applied or there is no electric field. So in thermal equilibrium, when there is no electric field, when there is no voltage, we know that voltage and electric field come from one another. So if you apply an electric field, it's the same as you're applying voltage. And if you're applying voltage, you produce an electric field. So they're the same. So let's assume that we don't have any electric field or any voltage applied. That is a situation which we call thermal equilibrium. So no electric or voltage is applied. Now, we know that if we have a semiconductor and there is no electric field applied, then we at a certain given temperature, what we will have is we will have electrons inside this semiconductor, okay, free electrons. They will move in different directions. They will move in this direction, 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 okay, but there is no current generated. They will just move thermal motion because they are heated, there is temperature, they acquire some energy, and then they move around. But they move randomly from one place to another, and they don't produce any current. The net current is zero, even though they move. That means the average motion in any given direction is zero. They move equally well in different directions and opposite directions. So their motion cancels one another. And in that case, their Vn, the average velocity of the electron, must be zero. Therefore, there is no current density, Gn. That is when you don't apply any electric field or voltage. They just move randomly, right? And the motion cancels out and you don't get any net electric field, current. The same thing for holes. If you have holes, you have holes moving arbitrarily in different directions, and therefore no net current. Now we want to turn on an electric field. So what will happen with the electric field? Now the electric field causes, let's say we're just talking about electrons. So we're talking about a semiconductor where we only have electrons. That is to say, N-type semiconductor. We have some background holes, but their density is very, very small. We might as well ignore it. Okay? So we're talking about a semiconductor which has only electrons. So what happens? What happens is we have Newton's second law. And Newton's second law says mass times acceleration of any object equals the force acting on the object. This is classical mechanics. I told you throughout, the previous lectures and the previous chapters that we need to use quantum mechanics. And here I'm writing Newton's second equation, which is a classical mechanics equation. So how come? How come? I told you also it's very laborious, very difficult to use quantum mechanics all the time. And so we're going to use an approximation, which is the effective mass approximation. And if we use the effective mass approximation for electrons in a crystal, then we have to use m star n, which is the effective mass for an electron. So the effective mass of the electron times the acceleration of the electron equals to the force applied on the electron. What's the force? The force is E, the charge, times the electric field. If you have any electric field, then we know that the force acting on the charge, E, is equal to the charge times the electric field. And we are applying an electric field here. This dV by dt is actually the acceleration. And this v is the velocity. So now if we have drift, if we have an electric field applied, then we don't have random motion, we don't have arbitrary motion of electrons. Now the motion of electrons is organized, is regulated by the electric field. The electric field makes the electrons move in one given direction, which is opposite to the direction of the electric field. So you don't have random motion anymore. The subscript n for electron minus E, the charge of the electron, dV by dt is the acceleration. remember, we're talking about a constant electric field E, which is an external electric field. And we're still using an approximation which comes from quantum mechanics, and that is the effective mass approximation that makes life easy for us. So this is a very simple equation to solve. If we want V, we just integrate the left-hand side with respect to time, and we will get an expression for V. So if we integrate and we take m star to the right-hand side, then we get V minus E, small e, the charge of the electron, capital E, the applied electric field, times time divided by m star n plus a constant of integration. Okay, so this is an expression for the velocity of the electron, and it's opposite to the direction of the electric field, because as you can see, you have a minus sign here, so meaning it's opposite. Now at t equals 0, okay, we have random motion, right, or random electron velocities. Okay, so the electron does not increase indefinitely. Now this equation tells us something very strange which we do not observe. It tells us that the velocity of the electron increases with time, right? And it increases as long as time increases, the velocity increases. So that means if I apply an electric field, applying an electric field is the same as applying a voltage. If I'm applying a constant voltage, that means a constant electric field, then the velocity of the electrons will keep increasing with time. But we know that the velocity affects the current density. We know that the current density depends on the velocity. So that means the current density increases with time for a constant voltage. But we never observe that. Yeah, I mean, you never have any electric circuit where you apply a constant voltage and you measure the current, and then you see the current increases with time. The current stays constant for a constant voltage. If you want to increase the current, then you have to increase the voltage. So what that tells us is that we should not allow this T to increase as we wish. So what happens is you will have an electrons moving, okay, opposite to the electric field. So if you have an electric field in this direction, okay, so the electrons would be moving this way, and then their velocity would increase with time, so they will all be moving this way here, okay, and their velocity increases with time. But what happens is this electron collides with this electron, a collision, because as they're moving, it's like people coming out from a football stadium. You know, they all come out. You cannot just speed up all the time because you have people in front of you. So you speed up, you collide with somebody in front of you, then you slow down. Then again, you find some space, you speed up, and then you collide with somebody, then you slow down. So this collision makes the electrons scattered back like this, but then they straighten up and go forward. So if we can calculate the average time between collisions as people are coming out from the football stadium, if we say that I make a collision as we move out every 2 seconds, then that means my speed increases, and then after 2 seconds I collide with somebody, I slow down to 0, and then again it increases 2 seconds, and then I collide with another person, and then it decreases to 0, and so on. Then I can think of an average time, which is the time t, I call it tau, the average time between collisions, and this average time may be 2 seconds. That's the time when I can have my velocity increases, and then it comes to another value. Okay, so if I use that concept, then I can write my velocity as this average time. I'm going to call it tau. Okay, So Vn is minus E, capital E, tau n over m star n. This tau n is the average time between collisions for electrons. So the velocity increases over this time, and then it goes back to a low value and then increases again. So this is my average velocity. Okay, so this average velocity can be written as in terms of some mu. Okay, I don't think this is written right. For some reason, the Greek letters do not show up. So this is mu. Okay, which is like a U, a curly U, mu n E. So again, one thing that I want to remind you, this constant is actually 0, because at the beginning of time we have a net 0 before the application of the electric field. As I argued, that you will have random motion, so you can set that constant equal to 0, and then our time t now changes to an average time between collisions, tau n. So we can take together all of these here, all these factors, okay, take them together, and instead of them put mu n. So our mu n is this quantity here. Okay, so mu n, which is, this is very inconvenient, you know, when you don't get the Greek letters. So Vn can be written in terms of this mu n times E. This mu n is all these factors here, E times tau n times mn. These are what I call mu n, right? So this is these three, which are E times tau n times m star n. And this mu n times the electric field gives you the average velocity. Okay? So this is a very, very simple theory which tells you about the mobility. Okay? This mu is called the mobility. The mobility is the ability of electrons to move, the ease with which electrons move. This ease with which electron moves depends on the average time between collisions and depends on the effective mass of the electron. So if the electron is heavy, then the mobility is small. So it is less easy for the electron to move. If the electron is light, then the mobility is high. The electron can move very easily. Tau, time between collisions. If the collisions happen after a long time, then the electron can move easy. If the collisions happen after a short time, then the mobility is small and the electron can move less easy. It's the same thing, a crowd coming out from a football game. If you have people in this crowd, heavy people, then they move slower. So their mobility is slower, less. If the number of these people in the crowd are smaller, so they have more spaces between them, then the average time between collision is large, therefore they can move easier. Okay, so if you have light people, okay, and if you have big spaces between people when they can move faster, and they can, you know, have a larger mobility. Similar algebra is applied for holes, okay? And for holes you get tau p, which is the average time between collisions for holes. And again, you have the effective mass for holes, okay? And again, you have the velocity of holes related to the mobility, mu for holes, okay? So the mobility for holes is again similar. Mobility mu b for holes is again similar to the mobility for electrons, except that the average time between collisions is now for electrons, and the mass is the effective mass for holes. And so now we have the hole mobility. So now we're seeing very important parameters. Remember, all of this is drift, motion in an electric field, drift of carriers. So we're coming up with the concept of average time between collisions, and we're coming up with the concept of electron mobility and hole mobility. All of these concepts we needed to have to determine the velocity, average velocity of electrons, as well as the average velocity for holes. Okay, so we can write the average velocity for electrons as simply the mobility of electrons times the electric field, and the average velocity of holes as the mobility of holes times the electric field. So now we have the mobilities, right? Then let me give you some experimental findings, what people found for mobilities. You know, we know how to get mobilities in terms of the average time and the effective mass. They found at room temperature, 300 Kelvin, in silicon, the mobility of electrons is 1450. And look at the unit, centimeter squared per volt per second. That is the mobility. And the mobility for holes in silicon, they found it to be 450. Okay? In germanium, we have higher mobility for electrons and higher mobility for holes. So that means maybe in germanium we have less, lighter electrons with a smaller mass, and we have longer time, average time between collisions. That's why we have higher mobility. Look at gallium arsenide though, 8500 for electrons mobility and 400 for holes. But it's interesting to compare the electron mobilities in gallium arsenide and silicon. You can see that in gallium arsenide, the electron mobility is almost 8 times higher than that of silicon, which is very significant. Mobility means the ease with which electrons can move. Then that means electrons can move 8 times faster in gallium arsenide than in silicon. Then that means the response time for any signal, the response time for current to show up, is 8 times faster in gallium arsenide than in silicon. So that is very, very, very important and very significant. It tells us that devices in gallium arsenide tends to be much, much faster than devices in silicon, because electrons can move faster. Okay, that is why very, very, key computers in the space exploration for NASA, for instance, they use computers made up of gallium arsenide chips. Why? Because they want very, very fast